All right, here we go once again. Welcome back to lecture 14. So today we're going to really start getting into Psychtoolbox and Matlab a little more deeply than we have before. We did a little bit of Psychtoolbox last week, but it was mostly me showing off graphical abilities that it has. So today, hopefully, we're going to do a somewhat more realistic demo that you could use for a psychology task and things like that. And hopefully you guys will get to kind of play along as I go. So before we get into that, though, let's click my clicker several times before it starts working. So this is kind of where we are for now. So we're kind of still talking about the basics of Psychtoolbox and graphics. Last time we showed you, we didn't have a lot of practice with it, but I did show you kind of some code for putting a picture up on the screen and moving it around and rotating it and doing all kinds of fun stuff, actually. Today we're going to talk a little bit, like in the lecture portion, about Matlab data types. We've talked about this a tiny bit before, but this is going to be a difficult thing for you guys, I think. So it's good to revisit it and talk about it a little bit more formally. And then we're going to try to talk about the topics of sound, keyboard, and timing. And again, we're not going to talk about everything that Psychtoolbox can do with regard to these topics, but I'm going to give you guys just a taste, show you how you can look up details on documentation, and then have you do some things in the problem sets, the last few problem sets, that will let you kind of build on this knowledge and build it up a bit more based on what we've done in the lectures. So far, problem set 7 has Matlab on it, but no Psychtoolbox. So problem set 8 will be the first time that you'll be actually writing Matlab code of your own and some Psychtoolbox code. And again, we'll try to start kind of small, modifying existing code, adding in small things, and then build up from there for the last couple of problem sets. Okay, so just to remind you all, problem set 7 is due next week. I think I said on Monday. I will try to get problem set 8 soon thereafter, or possibly even before it's due. This is not to make you guys feel like you have to constantly be working on problem sets, but I want to have them available for you as soon as possible because the semester is kind of weirdly compressed. I want you to not miss out on having time to work on them just because I haven't gotten to releasing it yet. So I will release it from afar and send you an email when it's released. What was I going to say? Oh, and my goal is to make these a little bit simpler and easier and a little bit more like tutorials than last semester because we don't have as much time. So I'm hoping they won't take quite as much time as some of the ones last semester. And again, I realize you have your projects and stuff to work on too. So I'm going to try to go easy on the problem sets. Now, next week, I am leaving the country tomorrow. I do plan to come back. So I will be coming back a week from tomorrow, but that means I'm not going to be here at our scheduled class time next week. So if people are desperate for more lectures on this stuff, or if we need to make up stuff at the end of the semester, we can schedule a makeup class, but I figure you guys could probably use a week off to kind of focus on building up what we've talked about so far and to work on your projects and stuff. Would people agree with that generally? So what I would suggest is, I won't be here to supervise you, but I would certainly suggest that you keep this block of time next week and come in here and either work on a problem set or just building up your knowledge of what we've talked about this semester, or work on your projects during this time. But I think it's probably best if we kind of just take a week off for now and don't add any new concepts so that you guys have time to kind of digest what we've talked about so far. So that's that. I have written your exam. It's a doozy. No, it's not. It's not that bad. But I have sent in your exam questions, and if the external examiners don't have changes, the exam is done. It is 2 hours. It's about 15 short answer questions. Short answer meaning like 2 to 4 sentences or so, and your choice of you write 2 essays with several choices for each essay. And just to let you guys know, you don't have to write any code on the exam because you won't have access to a computer, and they didn't really like that when I proposed that you guys might be writing code by hand. So what it will be is really questions on like theoretical stuff we've discussed, general programming concepts. I'll ask you to outline some algorithms, sort of the kind of stuff that you're doing on like problem set 7, where I'm asking you to like analyze little pieces of code and tell me what they do, to plan out an algorithm without actually writing the code for it, things like that, and then just information about general programming constructs I've asked you about, like differences between Psychtoolbox and PsychPy, differences between Python and Matlab, things like that. How functions work, how objects work, stuff, all these general concepts that we've been learning all along. So we can talk more about that when the exam is closer, but just thought I'd forecast that to you. So basically your final sort of test of programming skill in practice will be your projects, and the exam will be more about like what kind of theoretical things you learned and how you learn to think abstractly about programming. Okay. Any other questions from anyone before we jump into today's lecture content? Everyone good? Okay. So let's talk about data types a bit. We talked about this in Python last semester. We kind of reviewed the data types you know from Python. So switch into your Snake Python brain and think about what you know how to deal with in Python. So remember, we've talked about integers in Python. Integers are kind of special, and they're treated differently from another type of numbers, floating point values, right? So integers can only take on integer values. If you try to divide the integer 5 by the integer 2, you get 2, right, instead of 2.5. So, you know, integers are treated differently from floating point values in Python, where floating point values can take on any decimal value. We also talked about strings, right, which are pieces of text enclosed by quotation marks. We talked about Boolean values, true and false, right? Truth values, just simply true or false, which basically equates to 0 or 1. And objects, right? Which are things that encompass both other types of data and some functions that we call methods, right? So an object is something like a PsychPy window object that both holds information about the window, like where it is, well, window's a bad example, like its size, things like that, but it can also do things, right? So the window can like flip itself, for example. Or another example would be a PsychPy like image stem object, right? So an image stem knows things like what file name you gave it, what all its pixel values are, what its size is, and it can do things like draw itself, right? So objects are collections of data coupled with methods or functions that the object can do things either to itself or other objects. And then lastly, we talked about lists and tuples last semester, right, which are just ways of grouping together other data types or other variables, right? So if you remember, I grouped them together because they're used very similarly in Python, but the difference is that lists, well, one of these you can change and one of them you can't. Which of them, lists or tuples, is the one that you can actually change and add to? Raise your hand if you think you can change a list. Raise your hand if you think you can change a tuple. All right. Raise your hand if you forgot what those things mean. Okay, yes, so the couple of you that raised your hand for lists are correct. So you can change a list. Once a tuple is created, you can't actually change it, right? So we can say that lists are mutable and tuples are immutable. That's one difference. Another difference is that generally style recommends that lists be all composed of similar things, like if you have a list of all integers, that everything in it is an integer, whereas tuples are more frequently used to group together things like one integer, one string, and one floating point value, or something like that. But that's not a hard and fast rule. Sometimes you'll have lists that have different types of things in them. Okay, so that's all the data types we really talked about in Python, right? All the general sorts of data types. Now, data types in Matlab are somewhat similar and somewhat different, right? So as I've said before, like a million times, the weirdest thing to get used to in Matlab is that whether it looks like it or not, everything in Matlab is internally represented as a matrix, right? Matlab stands for Matrix Laboratory. What that means is if you've got a single value, what that really is it's a matrix that's one by one, right? That's one row by one column with one value in it. And you might say, what's the difference? And the difference is that, a lot of Matlab is based around the logic of linear algebra and matrix arithmetic. So when you start to consider that everything is a matrix, that sort of has some implications for the kinds of operations you can do on everything. And the idea is that nothing has to stay a single value. Like if you've got a single value, that's a 1-by-1 matrix, but you can always expand that matrix to be a 2-by-2, or a 3-by-4, or a 5-by-12, or a 6-by-10 by 11, whatever. So everything's a matrix, right? We've seen a little bit of this. We'll see more of it later. So advantages. One is that you can use consistent notation across data types. So for instance, I'll show you a couple of tricks here. So for this first little bit, we'll kind of dip in and out of the slides in Matlab. So I'm going to start up my Matlab here. You guys can try things like this out as you go as well, so you may want to have your Matlab started. So by consistent notation across data types, I mean something like, let's say I create a variable called myString equals, this is a string, something like that, right? And I create another matrix called like my numbers, and I put some numbers in there, and let's say 482, 6.3, 17, 9, that's fine. All right, so I've created these two matrices. One's called myString that has this text in it, one's called myNumbers. They look a bit different, and I mean, to some extent that's logical, right? Because you have to tell Matlab the string is a string, so you can use quotes to do that. For ordinary matrices, you use these square brackets, right, to enclose a matrix, just like you do in mathematics, right? Like usually, if you see in a mathematical paper a matrix, it's represented in big square brackets. But you can do some things similarly with this string and this numerical matrix. So, not to give away one of the questions on your problem set, but if you want to know like how big your string is, you can say size of my string, and it says 1/16. I won't tell you exactly what size does, but hopefully you can guess by doing this and doing what's in the problem set. Whoops, sorry. Oh, that was dumb. That's not what I meant to do. I meant to do size of my numbers, not my numbers of my string. Right, so you can see like the size of them, and because they're both matrices, the size is represented in a similar way, right? Because the string is we call this a row matrix, right? Because it's a row of, it looks like text, but it's really, you can think of it as a 1/16 matrix of characters, right? So there's 16 characters in it in a row. This numerical matrix is a row matrix that's got 6 numbers in a row, right? And if I want to do something like get the first 3 elements of each item, again, not to give away too much, one of the questions on your problem set, but I could say my numbers 1:3. That would give me the first 3 values in my numerical matrix, right? Or if I wanted to look at, remember 1, unlike Python, 1 is the first item in a matrix, not 0. If you do 0 through 3, it'll just give you an error. So if I want to get items 1 through 3 in my numerical matrix, I can do something like that. Or if I want to get items 4 to 5, I can do that, which is 6.3 and 17. But I can do the same thing with my string, right? So if I want to get the first 3 characters in my string, I can do my string 1:3, and I get the, which is the first 3 characters. If I want to get the 4th and 5th ones, I can do my string 4 to 5. It's tricky to see, but that's S space, right? Because it's this space is a string. So you can use the same notation to access different subparts of both numerical matrices and strings. And you can use similar notation for all kinds of things. So for example, let's say I want to add some values to my numbers, right? So my numbers currently has 6 values in it, but let's say I want to add a few more values to it. I could say something like my numbers equals, make little brackets here, right? Square brackets. And if I say my numbers, and let's add the numbers 11, -94, and 3.14. Okay, so now now it spreads it onto 2 lines, but it's really still, because it has to print it in 2 lines to print. But if you look at the size of it, it's clearer. that we now have a 1 by 9 matrix, right? Meaning 1 row, 9 columns. So in other words, it's just a row with 9 elements in it, right? And we started out with 4, 8, 2, 6.3, 17, 9. Then we added 11, negative 94, and 3.4. So if you put two matrices or some values from a matrix in between brackets, it'll join those together, right? It'll make a new matrix with all of the values in my numbers, and then these new values in the new matrix, right? And you can do the same thing with strings. So if you want to like join two strings together, you can say my string equals my string. What was it before? This is a string. And now it is longer. So what I've done is I've just enclosed my string and another string in square brackets. And now my string says this is a string and now it is longer, right? So again, we use that same kind of matrix style notation to both join together numerical values into a larger matrix and to join string or character values into a longer string matrix, right? Okay, so again, Matlab notation is very weird. I want to introduce you to it slowly. You will not understand all the subtle elements of Matlab notation for a very long time. Possibly. I still look up notation things in Matlab to this day, and I've been doing it for like a decade. So I don't want you to necessarily like 100% understand what we're doing here. The point is we can use similar notation for things as different as numbers and strings. And that can be very useful sometimes. In that we don't have to remember, like in Python, you sort of have to remember different operators. Like I think you can join two strings together with plus, which kind of makes sense-ish because like you're kind of adding them together. But you know, like you have to sort of remember that. Like in Matlab, oftentimes you can use the same notations for almost every different data type, which is super helpful. And it means you can do a lot of operations on things like strings that you normally just associate with numerical matrices, you know, by treating them like numerical matrices. Okay, so that's one advantage. I shouldn't have bothered to go into the slideshow because the next one is you can do very powerful parallel computations that are really easy to implement in simple lines of code. So, for example, let's see, how many numbers do we say we have in my numbers? We have 1 by 9. Okay, so if we wanted to multiply everything in the my numbers list by 3, that's pretty easy. My numbers times 3. Okay, so just to compare, so I didn't assign that to anything, so my numbers shouldn't actually change, right? So my numbers was 4, 8, 2, 6.3. My numbers times 3 is 12, 24, 6, 18.9, and so on, right? So in Python, there are ways to do something like this, but it involves like importing some modules that basically make Python act more like Matlab. By default, you know, if you had just a list of numbers in Python and you wanted to multiply them all by 3, you'd have to do some kind of for loop and step through that for loop, and for each item, you know, print out what that item is times 3, right? So what would take you, you know, 3 or 4 lines of code in Python, or at least, at the very least, 2 lines, depending on how efficiently you wrote them, you can do by just typing my numbers times 3, right? And similarly, if I want it, let's make a new set of numbers, so let's call it like more numbers. And I'm just going to set that equal to some random matrix that's 1 by 9. Again, you don't have to know all the details of how all these functions work, but what I've done is I've just created a matrix of random numbers, right? And it's, if I look at the size of more numbers, it's a 1 by 9 matrix. Again, meaning it's got 1 row, 9 columns. In other words, it's just a row with 9 items in it. So if I've got, if I want to add together my numbers and more numbers, it's as simple as saying my numbers plus more numbers. Okay? And I think we kind of demoed this at an earlier lecture, and we said, if you've got 2 matrices that are the same size, and you try to add them together, Matlab is smart enough to say, okay, I know that you mean add each element in matrix 1 to each element in matrix 2, right? So we add together 4 and 8.14 or 0.1847, we get 4.8147. We add 8 to 0.9058, get 8.9058, and so on, right? Whereas MATLAB is also smart enough, like up here we saw that MATLAB is also smart enough that if you try to multiply a matrix with more than one item in it times a single value, or add a single value, or subtract a single value, or anything like that, it's smart enough to say, what you mean by that is you want to multiply everything in that matrix by the same value, right? But anyway, the point is, again, if you were adding together two lists in Python, what you'd have to do is have some kind of for loop, get the first item in each list, add those together, get the second item in each list, add those together. Here, in MATLAB, you can just sort of add these two things together, right? So one thing about MATLAB is you should find yourself writing a lot fewer for loops if you want to do things like this. There are crazy things you can do with MATLAB once you really get comfortable with it. So, for example, let's make a slightly bigger random matrix of numbers. So let's call it numbers again or something. I don't know. So let's make it a 4x4 matrix of random numbers, right? So don't freak out because we're now getting into like a bigger matrix, but we've got right, just a 4x4 grid of numbers, random numbers between 0 and 1. But let's say these were real values. Let's say, let's say these are trials for 4 participants. Actually, let's make it a slightly different size just to make it more obvious. So let's say we have 8 rows instead of 4. So imagine this if this were data in SPSS. Maybe what we've got is we've got observations from, or maybe in Excel would be a better way to put it. Let's say each of these columns is a subject, and each of these entries in each column is, a reaction time for a task or something like that, right? So one thing we might want to do, if we have our data set up like this, is get an average for each column, right? That's a pretty common thing you might want to do, so that we have one average value for each participant. The way that you would do this in a lot of programming languages is to set up a for loop that steps through each column, and then inside that have another for loop that steps through each item in that column and adds them all up and then divides by the total number. In MATLAB, if you want to get the mean of each of the columns, you simply say mean, parentheses, numbers again. Mean is the function that calculates the arithmetic mean. Bam, right? So that's, take it for granted that the mean of this column is 0.4668, the mean of this column is 0.4253, the mean of this column is 0.5525, and the mean of this column is 0.5132, right? So if you're using MATLAB correctly, for things like, basic calculations and things like that, very often if you find yourself doing a for loop to kind of step through a matrix and do some calculation, there is a more parallel way to do it by just entering one command, and MATLAB will do it across the entire matrix all at once. And how it does that is magic as far as you care. Don't worry about the details, but it's pretty cool that you can do that, right? And just to sort of show you that, you can do this kind of any old which way. If you want to get the mean in a different dimension, so let's say I wanted the mean of each row instead of each column, that's easy to do too. I don't have to do anything fancy to transform it. I just add a parameter to the mean function, which says that I want to do it across dimension 2. Now, again, this is more than you need to know right now, but basically the idea is if you take the mean across rows, that's dimension 1. If you take it across columns, that's dimension 2, because, well, I'll tell you why in just a second. But if I take the mean across dimension 2, look, now I've got a column with the means from each row, right? So again, I didn't have to do anything fancy. I didn't have to set up for loops. I just entered one command, told it I wanted to take the mean across dimension 2, and I've got my mean in just one command. And it executes, in terms of computational time, this executes much more quickly than running a for loop and calculating each loop independently. Okay? Because for loops are very slow. If you can parallelize mathematical computations like this, it's very fast. And again, that's why MATLAB exists, is to do lots of calculations on these massive data structures very quickly. Okay, so just as a side note, if you wanted to know why it works the way it does, if we remember what the size is of this numbers again matrix, it's 8 by 4. That means that 8 means it's 8 rows tall, and the 4 means it's 4 columns wide. So one thing to keep in mind whenever you whenever we're working with two-dimensional matrices, it's always rows by columns, rows by columns, 8 rows by 4 columns. I say this many times because you've got to drill it into your head. You will mix it up otherwise. That means that the first dimension, dimension 1, is rows, dimension 2 is columns, right? So 8 rows, 4 columns. If I want to get the mean across basically, if I want to get the mean across columns, I specify dimension 2. All right, anyway, that's more than you need to know, but I'm trying to sort of sprinkle this stuff in kind of slowly so that it doesn't blow your mind too much when we start really using this stuff. Okay, another thing is very sophisticated indexing methods for accessing subsets of data. That I sort of already showed you. So indexing just means if you've got a list or a matrix of things. Python sometimes calls it slicing. You saw the colon operator in Python was also used for slicing. You can do some very fancy styles of indexing in Matlab. So I'll show you a few examples. So let's clear this out. Show you. So let's call it my nums, whatever. And one thing I haven't quite told you how to do yet is the colon can be used for a lot of things in Matlab. I asked you about one of those uses in the problem set, but this is a slightly different use. If I do 1:100, it sets this variable equal to the numbers 1 to 100, kind of like the range operator in Python. So now I've got this variable called mynums, which is a 1 by 100 row of the numbers 1 to 100. I can do some fancy indexing things. So one thing I can do is, like if I want to get every third value in this matrix, I can say, well, if I wanted to get like, let's go slow. If I want to get like just the first 10 values in the matrix, well, actually, let's do values 11 to 20 to make it a little more interesting. Now that's just going to be the numbers. Whoops, my nums 11 to 20. That's just going to be the numbers 11 to 20 because the first item in this matrix is 1, the second item is 2, and so forth. But let's say I want to get every third item in this series between 11 and 20. I can add another colon in the middle and say 11 by 3s to 20, which means 11, 14, 17, 20. Basically, that means start at 11, go by 3s, end at 20, right? So that's kind of cool. You can do fancy. That's a fancy way of indexing this. And you can do all kinds of other stuff too. So this is getting a little too detailed, but if I wanted to think of this 100 element list a different way, let's say I want to think of it as a 10 by 10 matrix instead of a 1 by 100, I could say my nums equals reshape my nums and tell it I want it to be a 10 by 10 matrix now. And it gives you my nums reshaped into a 10 by 10 matrix. You see that those elements get put into rows, or sorry, get dumped into each row first and then go onto a new column, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1 to 20. And then you can do crazy things like, we can say like, let's say I want to access the 5th row, the 7th through 9th items, for example. Okay, 1, 2, 3, 4, 5. 5th row, that's 5, 15, 25, etc. 7th through 9th items should be 65, 75, 85. Okay, so again, you don't have to get how it all works. The point is you can do some pretty fancy, sophisticated things to index or access subsets of your data. And again, you don't just have to do this with numbers. You can do this with strings and all kinds of things like that, which can occasionally be very useful. Okay, and the last thing is that it's a more accurate reflection if you really know how these things are implemented in the computer hardware. Treating everything as matrices is actually a pretty accurate way of reflecting how data are stored in memory. I mean, maybe there's value to that and maybe there's not, but you can get sort of closer to the computations if your data storage method sort of reflects the way that information is stored in memory. Okay, so anyway, one thing I wanted to talk to you guys about is the equivalence in Matlab of Python things. Okay, so I'm going to go through this kind of quick because we already did several demos. Hopefully you could step through with me because I want to get into the actual coding. We may not get done today. Okay, so first of all, numbers, integers, and floating point values. We've talked about this before. Just to review, Matlab does have a way to create matrices that are purely integer values, but we will hardly, if ever, use them. Okay, so you don't have to worry about them for the most part. Typically, by default, every number you use in Matlab is stored as a floating point number. It's specifically called a double precision floating point number, meaning it has twice the memory usage, but also it's more, it can represent more decimal places. And they call these doubles. So whenever you see, like in your Matlab workspace, if you look at what a variable is, like the variable mynums, it says 10 by 10 double. What that means is it's a 10 by 10 matrix of double precision floating point values. Even though, as we see, everything in here is actually an integer value, right? So we could have just represented this with an integer data type, but Matlab by default calls them all floating point or decimal numbers, which has some strengths and some weaknesses. Now we can still use them as integers, and I think I've shown you a couple of functions before, like ceiling, floor, seal technically, floor, and round, to eliminate fractional parts of things. So, in Python, if you wanted to do, 5 divided by 2, you get 2 if you didn't specify that these were floating points. Here, it has no problem saying 2.5, but if you wanted to round down and get rid of the fractional part, you can just say floor of 5 divided by 2. Floor means, again, think of the next number down as the floor, the next number up as the ceiling. Floor means what's the floor of this non-integer value, right? So the floor of 5 over 2 is 2. If I wanted to get the next number up of this floating point value, I could do ceiling of 5 divided by 2, that's 3. And if I wanted to, let's do it as 5 over 3 instead. If I wanted to just round it to the nearest integer, rounding 5 divided by 3 gives me 2, right? Whereas if I round 7 divided by 3, that's also 2, right? Because that would be 2 1/3. Okay, so there's various things you can do to treat things as integers. And if we want to test and make sure that's equal to 2, it gives us 1, which means true. The only real problem, there are only a couple of potential problems with storing everything as a double. One is that it does use more memory than integers. That's usually not a problem in the modern world unless you're working with just massive data sets. So we don't usually have to worry about memory. The only other difference is there is some limited precision to floating point numbers. So an integer is exact, right? If it says it's 122, it's exactly 122 because it's unambiguous. Whereas floating point, has a limited number of significant digits. And so with integers, for a certain amount of memory, you can represent a certain number of integers. The problem with integers is you run out of a range. Floating point numbers can essentially express a basically infinite range of values, but with limited precision. So if I ask you, is 2 equal to 1.9, you should get no. But if I add enough decimal places, I get a yes, right? So, and I don't take the slide as, okay, right? So somewhere in that range of decimal places, we see the difference in how Matlab is able to distinguish two numbers, right? So as long as you don't care about more than about, 10 or so decimal places, it's fine to use floating point numbers for everything, okay? So that's just something to be aware of. So effectively, everything in Matlab you can treat as a floating point number. Okay, strings. As you've seen, Matlab does have strings. The notation is very similar to Python. In Python, I generally recommended you use single quotes for strings. In Python, you can also use double quotes. In Matlab, you can also use either single or double quotes to enclose strings, but for various reasons that are not worth explaining, it is generally better to just use single quotes for everything in both languages, so that because it's better in Matlab, and it's better that you don't get confused between Matlab and Python. So generally, just use single quote strings for all strings. So that's how you indicate that something is a string. You put it in quotes. That seems reasonable. Like we saw just a few minutes ago, strings are really matrices of characters. And so what that means is typically, like we saw before, a string is usually a row vector, but strings can also have more dimensions, right? So we did a demo like this a few days ago, or a few weeks ago rather, but just to reemphasize, let's say my stir equals this is a string. Let's call this one string 2 equals this is another. Let's see if this works. Okay, so I don't have the same dimensions on this is a string and this is another. So size of my stir, that's 16 characters long. Size of stir 2 is 15. Okay, so let's make stir 2 more enthusiastic. This is another. So now it's 16 characters long. And now what you see I was trying to do is make, let's call this stir 3, make a third string that is these two strings on top of each other. So if I get the size of string 3, I get that it's a 2 by 16. It's a string, but it's really a 2 by 16 character matrix, right? The key thing here, so I did a few things that are worth noting here. One thing I did is, you'll notice I used a semicolon here when I used these square brackets to combine two strings like I did before, but instead of separating them with a space, I separated them with a semicolon. And what that means is, semicolon means like new line of the matrix, right? So in other words, what I'm saying is I really want these strings to be stacked on top of each other, not put out horizontally, because like if I didn't have a semicolon here, I'd get this. This is a string, this is another. I would join them horizontally, but if you put a semicolon between them, it implies a new line in the matrix and that you want to stack them on top of each other. Okay, so that's one thing we did here. The other thing to note is that this did not work when the strings were not the same length, right? Because in a matrix, one disadvantage of having everything stored in a matrix is a matrix can't have any empty values, right? A matrix that's 2 by 16 has 2 slots by 16 slots in it, and something has to be in every slot. Now that thing could be a space, it could be a 0. If you have a numerical matrix, there are special things to indicate like a non-number value, but something has to be in that slot. You can't have unoccupied space in a matrix. So one disadvantage is if you're trying to make a two-dimensional string for some reason, every row of the string has to be the same length, right? So that's just something to keep in mind. And you know, you could make this as high dimension as you want. So so let's see. We could say string 3 is my string, string 2. You can even add another string literal. So like blah, blah. Let's see if that's enough characters. Let's see. Do I have too many or too few? Probably too many. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No, not enough. Okay, right. So if I get the right number of characters, I can join these 3 strings together, make a 3 by 16 string, right? Or a 3 by 16 character matrix. I recognize that it would not be necessarily apparent to you guys why it's super useful to be able to do this, but it can be useful in certain contexts. Well, one way, actually, I can tell you one. One way, for example, would be if you're doing a problem like problem 3 of your problem set, which is to build a Latin square. Maybe you want to name your conditions A, B, and C. You could have a 3 by 3 matrix of characters, A, B, C, CBA, whatever, right? So that would be one case where you might want to have a two-dimensional string. Okay. Boolean values, just going quickly. Remember, Boolean values are just true or false. Matlab does have a special data type for Boolean values known as a logical matrix. You've already seen that we just call them true and false like in Python, except that in Python you capitalize them, in Matlab they're all lowercase. Logical matrices are just matrices of true or false values, and these are really just 1 and 0, but they are interpreted, especially by Matlab, as being logical values. And that leads to it being able to use them in some very powerful ways. I know I said I wouldn't show you this, but do you guys want to see why this is cool? If this blows your mind, just like put your fingers in your ears and hum for about 2 minutes. This is why this is super cool. All right. All right. So let's just say we have a participant that's just done a task, and we have a list of response times. Let's just make some up, like point, point. Actually, let's make these in a row so they're easier to see. Or sorry, make them in a column so they're easy to see. So I'm putting these vertically. What's that? That would be fine too. Whoops, what did I do? Oh, I didn't put the semicolon here. Okay, so I've got 4 RTs here. Let's say, here's another good case where you might want to use a string matrix that's a little bit different than the standard horizontal kind. Let's say I have correct responses is a column of characters. So let's say they use the Z and X keys to say yes and no to something. So Z, X. Let's say maybe the next one's an X too. Okay. Whoops. What did I do that time? Oh, I didn't have the equals in there, sorry. Correct responses equals that matrix. Right, so you've got a vertical matrix of characters, and let's say actual responses, so this is where we record the actual key presses, equals, let's say they got the first one right, the second one wrong, and let's say they got the third one right and the fourth one wrong. Okay? So one reason that logical matrices are very powerful is if we want to see if each of the correct responses is equal to the actual responses. Remember we said like mathematical operations can be done massively across an entire matrix. Well, so can logical operations. So that means like if I want to see if actual responses are equal to correct responses, I'm putting in 2 identically sized matrices. Matlab knows what that means is I want to test equality at each one of those items, and I get a logical matrix, so I can call this accuracies equals that. Now if you look at what it calls accuracies, it says accuracies up here is a 1×4 logical matrix, right? Meaning it can only be 1 or 0 or true or false. Now what's super cool is if I want to get the RTs only for accurate trials, I can actually use, I can actually use accuracies as a way of indexing my RT matrix, and I only get the RT values where there's a true position. So like if you see RTs by itself is 0.9290, 0.8380, 0.7829, 0.2765. Accuracy says the first and third trials are accurate. If I put RTs parentheses accuracies, I get only the values for the first and third trials. I know this is a little mind-blowing. But the idea here is, now imagine you had 500 trials. You don't have to have some for loop checking each trial to see if it's accurate. You just say, and you could actually do this in one line of code really, because I could just say, show me the RTs where actual responses equal correct responses. And it gives me the 2 lines where that's the case. So it's not that impressive if it's only 4 trials and you get 2, but if you're doing this over hundreds of things, I mean, you could do this for 1,000 subjects, you know, with 500 trials each in that same one line of code if you had everything in the right matrix, right? So if that blows your mind, don't worry about it. The point here is there are some ways that it can be very useful to have your logical Boolean values in a matrix. And there are some very powerful ways you can use them when you know what you're doing with them. Okay. But for the moment, you're mostly going to encounter Boolean values just as true or false. Okay. Don't worry, I won't ask you about that if you're totally confused. but it's fun to play around with. You can do some experimenting on your own. Okay, objects. We said in Python pretty much anything can be treated as an object. In other words, even like integers and strings can do things to themselves or other objects. Matlab does have some support for object-oriented style programming, but we are not going to be using it. So we'll be doing purely procedural programming, meaning we'll have functions, and we will put variables into functions and get outputs out of functions, but our variables are not going to be objects with methods of their own. In other words, they won't be able to, variables don't do things, right? Variables just have functions done to them, and the functions produce new variables, right? Now, one thing to note is that one thing that we use an object for in Python is like window objects, right? So we create a window object, and then we can tell that window object to like flip itself or whatever. Sometimes Psychtoolbox creates things that seem like objects. So like Psychtoolbox, we have done things like create windows, but they aren't really objects in the programming sense because they can't do things, right? So in Psychtoolbox, what you really get when you create a window is what's called a reference or a pointer or a handle, which actually technically mean different things, but for our purposes just mean what you really get when Psychtoolbox creates a window is you get a number. It's like when you take your coat to like the dry cleaners, and you give them and you get like the ticket. You know, that ticket is not a coat. That ticket is just a number telling you what coat is yours, right? So what happens when you create a window with Psychtoolbox is you come to Psychtoolbox and you ask for a window. Psychtoolbox creates a window object basically within its own code, but it worries about all the memory associated with the window. It worries about all the information the window has to handle. It only gives you back a number that's like, next time you need to use this window, you just ask for number 7, and I will do everything you need, right? Which is why when we do stuff with windows, like flip them or whatever, we don't say mywindow.flip. We say screen. We use the screen function and tell it to flip my window, right? And then Psychtoolbox just handles everything else for you, okay? So that's the difference. So we won't be using any sort of object-oriented notation in Matlab. Okay, last thing I think. Well, nearly last thing. Matlab, we already said, has no real need for Python-style lists and tuples because everything's a matrix, right? So even if it doesn't look like a list, everything is a kind of list or a kind of matrix in Matlab. However, most Matlab matrices have a restriction that Python lists and tuples don't have, which is that they have to be the same type of data, right? So if you have a matrix of doubles, you know, numerical values, it can only have numerical values in it. If you have a character matrix or a string matrix, it can only be character data, right? If you have a logical matrix, it can only be logical data. Now in Python, like we said, style generally recommends that you use lists for similar information and tuples for grouping different sorts of information, but it's not a firm rule. It's not a feature of the language. It's just a stylistic thing. This is helpful because it helps speed up computations for numerical data. So Matlab doesn't have to go through and check everything in a matrix to see what kind of data it is. So this is why Matlab is really optimized for fast computation. But there are occasions where you want something like a list or tuple where you want to group together different types of data. So you might want to package together a string and a number and a logical value all together. For this, Matlab has a very special sort of matrix called a cell matrix. I was going to hold off on telling you about these for as long as possible because they are little, kind of tricky little guys. But they're going to come up in the code today, so it's time to reveal them. So basically, cell matrices are a special Matlab matrix in which each element can be any data type. And actually, strictly speaking, what a cell matrix is a matrix where each element is another Matlab matrix. So that means it can be a number, it can be a string, it can be other cell matrices, anything. So it has a slightly different type of notation. So normal matrices in Matlab use these square brackets, and you use these square brackets to create them, and then you index them with parentheses, right? So if you want to get one of the values inside a regular matrix, you use round brackets or parentheses. If you want to describe or define, a matrix initially or group things together, you use square brackets. Cell matrices use curly braces, right? Like here, whatever you want to call them. I call them braces or curly brackets. They use those for grouping, and then you can get items out of them with either the curly brace notation or the parentheses, or or round brackets notation. Those notations are different, but we won't worry about the distinction just yet. You will need to worry about it at some point, but not just yet. So let me just quickly show you an example of a cell matrix, but you'll get more of an example when we get to the actual code. So let's say I've got my RTs. Let's say I've got my string. Okay, let's say I want to, for some reason, I want to group these things together. So let's call this like my cell equals curly brace, my string and RTs, close curly brace. My cell is these two things, right? So it shows you that I have, this is a string, and it tells me, it doesn't tell me the actual values, right? Because it can't print that easily, but it tells me that the next thing in the second position is a 4x1 double matrix, right? And if I look at the size of my cell, it's a 1x2, right? So what that means is the cell matrix has 1x2 items in it, right? Like one row, two columns. Now each of those, like I said, is a matrix of its own with its own size. But if you get the size of the cell matrix, it just tells you how many other matrices are inside the cell matrix, right? And I could put some other stuff in there. I could say my cell. So if I want to add an item to the cell, this is something we haven't quite done yet, but I think it might be in your problem set a little bit. But if I want to say like the third item of the cell, let's set that equal to blah blah, another string or something like that. I can do that too, right? So I can add on to the cell. That's all fine. I can put as many items into the cell as I want, right? Now if I want to get an item out of the cell, that's where let's call this like blah string. If I want to get that blah blah string out of here, I say my cell curly brace 3, right, for the third item. And I get blah string is equal to blah blah, right? And we don't need to exactly get in just yet as to when you would use round brackets or parentheses, I don't think. We'll get into that more later. So for now, we're going to use curly braces all the time for both putting things into cells and getting them out. We'll worry about the rest later. Okay, if that's confusing, that's okay. We'll get some practice writing some code with this, and we'll always have the podcast. And we'll talk about this more as time goes on. Okay, so for today's demo, maybe I'll introduce the idea, and then we'll start writing the code after a little break. So I was thinking about a good demo yesterday when I was frantically writing this lecture that would let us practice sound and keyboard and timing and all this stuff all together. So do you guys remember the McGurk effect from second year? Those of you that took second year cognitive, maybe. So sorry, this is, if you're listening to the podcast, turn your volume way down right now because we're going to make some loud noises. But if you guys remember, here's a video of the McGurk effect if you don't remember it. All right, you guys remember this from last year, maybe? So what syllable do you think this guy is saying? All right, so now close your eyes and keep listening. Does that change what syllable you hear? Hopefully it does. Okay, so if you guys remember, the McGurk effect is the idea that what's really happening is the guy's saying ba, but his mouth is making the video is of the guy saying ga. And what happens is when your brain is presented with conflicting sound and visual information of someone speaking, in this case it kind of fuses them together and makes an intermediate sound, which is da. Okay, so probably most of you heard da, but what he was actually saying when you closed your eyes and lost the visual input was ba, right? Okay, so anyway, this is sort of a dumb little experiment. This is mainly just to illustrate, but you know, it could be interesting maybe if we did it just right. So a question I was asking is, could like a visual context like printed text also affect people's decisions about what simple sounds they're listening to? So, you know, maybe you hear ba, da, or ga while you see one of the words ba, da, or ga printed on screen. Now, I've tried this already, and it turns out that obviously, like, you still hear what you hear, but, you could ask if it slows you down to get an incongruous printed word or whatever, even if you're just mainly trying to listen for the sound. So we could, ask whether the agreement or disagreement of the sound with the printed word affects your accuracy or response time. Or if we wanted to get really fancy, if we have more time, or maybe next week, we could even blend sounds together to make an ambiguous sound, and then see if the printed word influences your behavioral judgment as to which sound it is. So anyway, that's the demo we're going to try here. Again, if you're on the podcast, turn down your volume. There's a video I found on the internet when I was sort of Googling the background of this that sort of illustrates this principle, sort of. So listen very closely to this video. Okay, I have no idea who made this video. But maybe, I don't know how much this works for you guys, but the idea is that they're saying the same syllable, but depending on whether they show you bills, bales, pails, or mayo, it kind of sounds like all four of those words, right? So bill, bale, pail, mayo. The idea is that, visual context can influence sound perception. Although I don't know if these were scientists. I think these were just odd people that put this together. So anyway, when we come back, we'll do a demo where we look at doing audio stuff. We'll look at presenting text. Not so much pictures, but we did pictures last time. And also look at things like monitored keyboard input, getting input and getting response times. And hopefully just generally play around with Psychtoolbox a bit for the last hour or so. And if we don't have time for it all, that's okay. We'll get to what we get to. Okay, questions before we break? Okay, so here we go again. This will be the demo for Lecture 14 here. And I've just put those WAV files for you on the Google Drive of those ba, ga, and da. Actually, if you want to, you can play them if you want, or I can play them on the podcast again. If you're listening on the podcast, every time I'm about to play a sound, it's going to be loud for you, so prepare to turn the volume down. So let's open this with Audacity is probably the best. So if we want to hear what these sounds sound like, well, soon we'll be able to play them with Matlab, but here's an example.
Ba.
Right? So I just generated these artificially with the Mac voice, okay? Oh, actually, let's leave that up, because I'll show you something. Oh, crap. Sorry. Let's open that with Audacity instead. So here, just for your reference, is what that sound looks like, right? So this is an Audacity, a music editor. Where's my zoom in guy? You can see, all right, this is what it looks like when someone says ba, right?
Ba.
That's what the sound wave
Ba.
looks like. Okay, so no changes. Let's get in and write some actual Psychtoolbox code. I'm going to go into a special folder for just this week's code. Again, you need to keep in mind, just keep everything in whatever folder you're going to be in. Like, you need to be in the folder with the WAV files in it in Matlab. When in doubt, just put everything in your Documents Matlab folder, and your life will be easier, unless you can get used to switching directories within Matlab. Okay, so let's edit a new code file. I called mine McGurk demo, even though it's not really a McGurk task, but it's sort of McGurk-ish. So I'm going to edit McGurkDemo.m. Remember, I told you that one great thing to do is always to make everything, all of your Matlab scripts, functions, even if they don't need to take in or spit out any values. That'll make your life easier. So I'm going to call it function McGurkDemo. And we're going to try to do this very incrementally so that you guys can kind of test out as you go. So the very first thing we're going to need to do is just figure out how to play a sound in Matlab. And actually, we can kind of do some of this on the command line just to illustrate it. What I'm going to do is clear all my variables so you can see that I have nothing in my workspace now. We can do this in Matlab, but we can do it with more precise timing and everything in Psychtoolbox. But some of it we'll do in Matlab and some in Psychtoolbox. So the first thing we're going to need is there's a function called waveRead. if you do help wave read, WAVREAD, it'll give you more information than you probably strictly wanted about a wave file that you're going to read in. So we'll need that to read in a wave file. That's the easiest format to read from Matlab, so we're just going to make everything wave files. And you see that wave read can return up to, I think, 3 outputs. One of which is the actual sound data, one of which is the sampling rate, and one of which is the number of bits. You don't need to know exactly what those mean, but let's just try that on the command line, and we'll see what kinds of values we get from wave read. So let's call this sound data sampling rate in bits equals. So remember, that's a way that we can, and actually it's best practice, I believe, to separate these with commas, but you don't technically have to. So remember, that means we're going to get 3 output values from the wave read function, and all you have to put into wave read is, the minimal thing you have to put into wave read is a file name. So let's put in ba.wave as a string. Now remember your semicolon, or this is going to produce some really long output. And hit enter, and you should be able to have read in that wave file. It only takes a second because it's a very small file. And it tells you that n bits is 16, sampling rate is 22050, and sound data is a 9537 by 1 double, meaning basically what this means is 16 bits is a measure of the quality of the data. So CD sound, if you guys remember, a compact disc is like a round thing that you can use to make MP3 files. A CD quality sound is stereo sound, 16 bits at 44,100 samples per second, meaning that you get that wave is made up of 44,000 and change pieces of information per second, right? Now our sampling rate is half of that, but that's still pretty good. Quality is high, and sound data is some list of numbers that represents that sound wave, right? And it's a 9537 by 1 double because it's a mono sound, meaning like we don't have left and right channels. It's only a single channel of sound, so it sends out equally from the left and right speakers. Okay, so the main thing is our sound data, and then we also have this information because if you get the wrong sampling rate or the wrong number of bits, your sound is going to sound funny, right? It's like if anyone's a hipster and has like record album, you know that if you play your record, your LP on vinyl too fast, you get music that sounds like the Chipmunks, right? And same thing here. If we have a sampling rate of 22050 and think it's sampled faster than that, we should get chipmunk voices. And we can actually demo that if we want. So, for example, so Matlab's built-in sound function is, I believe, called, should look this up beforehand, yeah, but it's called sound. So you see that what sound uses is you give sound, conveniently enough, the 3 things that we just read out of this file. Y represents the sound data, sampling frequency, which we called sampling rate, and then a number of bits. And you could just send in 1 and it would guess at the other values, but we want to probably give it all 3. So if we say sound data, sampling rate, so we just give it the 3 pieces of information we just got from the file. Warning to the podcast, noise coming in now.
Ba.
All right. If you guys want to turn up the volumes on your PCs and try this, you should be able to get the same thing. Now, if we wanted to see if we get chipmunk voice, if we try to play it at a higher sampling rate, there shouldn't be anything stopping us from doubling the sampling rate. And you could do, you could do some things like you could say, well, let's say the data were sampled at 30,000 samples a second.
Ba.
Right? You can raise the tone versus the real sampling rate.
Ba.
And if you want to go like down to like Barry White frequencies.
Ba.
Okay, so that doesn't really matter. The point is, you have to tell any sound function, like not only just a bunch of data, but you have to tell it, the quality of the data and how many times you have sampled the sound wave per second to make sure you're not playing it too fast or too slow. Okay. Okay. Have you guys tried? Have you guys successfully played sound on yours? Or are you too afraid to try it? Let's hear a chorus of ba's from the audience. All right, well, I'll give it a second for you to try it. But anyway, so that's pretty easy, but the one problem with this is MATLAB's built-in sound function is not very accurate with regard to timing. So we're actually going to need some slightly more sophisticated functions for Psychtoolbox to play sound that we're going to use. But as you can see, it's pretty easy. 2 lines of code is enough to read in a sound file and play it. So that's pretty good. Anybody got it playing? I think I heard it, right? Okay, people got it working? Okay, so that's basically what we're going to need to do. So let's do a couple things here. Let's do this real slowly. So let's define a couple of initial values. So let's call one syllables. And I'm going to make what I just told you about before the break, a cell matrix. And ba, da, ga. I'm going to make a cell matrix with 3 strings in it that lists the possible syllables in this task. And the reason I'm going to put this in a cell matrix is because these are actually all the same length string-wise. So I could have made a string that's like a 3 by 3 string and represented this set of data the same way. But, you know, if I had some other syllable, like Sha or something like that, you know, that I needed more syllables to or more letters to represent. Remember, a matrix, a character matrix, has to be the same. Each row has to be the same length, right? So it's maybe easier to have a cell matrix with 3 elements in it, right? Now, one neat thing that I can show you that you can do in Matlab, if you want to test out a line of code you've just written into your file, you can highlight it and right-click and say Evaluate Selection, and it will actually type that for you into the Matlab command line. So now I've just created a variable called syllables on the Matlab command line, which is nice if you want to test out code and copy. It's easy, faster than copying it back and forth between your code file and the command line. So you see I've got this matrix that's got ba, da, and ga in it. So what we could do, for example, is randomly select one sound from this the syllable list every time and play it, right? So let's also decide how many times we want to do this. Let's set our number of trials. Let's just start off with 10 trials for now. And just to prove that we can do this, let's make this a real simple task for the moment and then gradually build up the complexity as time goes on. So let's first do it without any Psychtoolbox at all. So let's do a for loop. I like to call my loop counter I, but you can call it whatever you want. And I is going to equal 1 to n trials, which just means we're going to loop through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? This is how you do a for loop in Matlab. And what that really means is, by the way, now that you're sort of getting used to Matlab notation a little bit, if I do like 1:10 in Matlab, what that really means is, like I showed you before, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So what this is really saying is for I equals each element in the matrix generated by 1 to 10, or 1 to n trials. So each time it's going to be a new element in that matrix. Let's say, let's call it sound num equals, and we need to generate a random integer from 1 to 3. Do you guys have, if you type in, try this for me right now, capital R-A-N-D, whoops, sorry, type in Randy parentheses 3. Do you guys have this function in your, okay, so this is given to us, I think, by Psychtoolbox. Just wanted to make sure you had access to it. So Matlab doesn't have a built-in way to generate random integers. It's pretty easy to do it on your own. But if Psychtoolbox gives it to us, we may as well use Psychtoolbox's version. So Randy3 gives us a random number between 1 and 3. So if we do this a bunch of times, we should get, 1, 2, or 3. Where's our 2? Okay, there. Right. So let's pick a random sound number that we're going to use to select a random syllable. So let's call that Randy. Now, if we want to make this not dependent on, I could just put a 3 in here, but then what if I decide to add a 4th syllable to my code? Let me just put a little note here. End of general settings. So we're going to put all the settings up at top, and then the real code below. Okay, But what if I add a fourth syllable in here? I'm going to need to remember to update this 3. So a better way of doing this probably is to specifically put a variable in my code that is how many syllables we have. And in this case, it's pretty easy to use a Matlab function called length, which is the same as, I think it's called len in Python. That tells us the length of the syllables list, okay? So since we've got 3 syllables in this cell matrix, length of syllables is going to give us 3. Note that length gives you predictable results if you've got something that's all in a row or all in a column. If you've got a more complex matrix, like a 5 by 2, it'll still give you a value, but that value is the longest row or column or whatever. So if you've got a 5 by 2 matrix, length of that is 5. But length is most useful, obviously, when you have just a row or a column matrix. Okay, so instead of 3, we could say, let's generate a random number between 1 and n syllables. Remember those semicolons after pretty much every line, just to suppress output. Okay, so we have a number of the random sound, and of course then we have to figure out how to play a random sound. So we could do this a few different ways. Let's do this a kind of dumb way and then make it more sophisticated as time goes on. So one kind of dumb way is, let's go back to our history, copy this line of code we used to read in a wave file, right? So we said sound data sampling rate number of bits equals wave read ba.wave. So now what we have to do, of course we don't want to just tell it ba.wave. What we want to do is take our sound number and pick one of these 3 things. So we can do this by saying, let's call it file name equals, and this again is where it's kind of convenient to treat to use matrices. Now watch what I do here. File name is going to equal, I'm going to make a matrix that joins together 2 strings, and the first thing is going to be syllables curly brace sound num. Right, so sound num is a random number from 1 to 3. Syllables brace that is going to give me ba, da, or ga, right? Because it's going to be syllables item 1, 2, or 3. And then I want to add, since I've named these ba.wave, da.wave, and ga.wave, it's easy enough to just add in .wave to join that string with the string period WAV, or full stop WAV. And that's created a variable that's a string representing the file name, right? So then I can just replace the literal file name here with the variable that I called file name. Okay, so in theory, that should read in some sound data on each trial. Then what we can do, let's first of all just use the dumb Matlab functions and then gradually get more sophisticated. So we call that function sound. So we give it the sound data, the sampling rate, and the number of bits. So again, one nice thing about having this command line and this nice graphical interface is you can go back and forth very easily copying and pasting lines, as long as you remember to keep all your variables named the same. So we could do that, and we might want to wait a second or so in between sounds. So let's add in, I think I showed you this before from Psychtoolbox. This is a Psychtoolbox function. Remember, Psychtoolbox functions are easy to recognize because they are usually capitalized and Matlab functions are not usually capitalized. So just for the moment, let's just wait 1 second in between each sound, just to see if we can get this task to play 10 sounds in a row, randomly selected. Okay, so this should take about 10 seconds. If we've done it right, let's see if this is right.
Ba. Ga. Da. Ga. Ga. Da.
You can
Da.
use this length of
Ga.
time to try out your own.
Da. Da.
Okay, so it worked, right? Yay. One thing you'll note, by the way, I don't want to blow your mind here, but I need to make this longer to make it. So let's play sound data again.
Ba.
All right, so that was our ba that we read in. One thing to note about the Matlab sound function that is undesirable, let's make it play the sound 3 times. And let's make it 4 times. Okay, so what I did is I just made a little matrix in there that is sound data added to itself. Oh, shoot. But I want it to add up vertically, not horizontally. Okay. So I just basically repeated sound data 4 times, so it's going to go.
Ba, 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 ba.
That's kind of a good beat, actually. The main point is, look what happens in my code. Look what happens when I get my cursor back so that I can do more stuff when I hit this. Okay, so here it goes again. Same command again.
Ba, 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 ba.
Okay, I don't get command back till after the sound finishes playing, right? That's actually not super desirable because in Psychtoolbox, what we probably want to be doing is we probably want to start output playing and then have our code keep running again so that we can be drawing stimuli or whatever, right? So we can't really use the Matlab built-in sound function very well because it halts the whole program until the sound finishes playing. And it, like I said, it's not very precise timing-wise. So the first thing let's do, and so the reason I noticed that actually is because I put this waitsex in here, right? One of the best function names in the world. I put waitsex in here, but what you might have noticed is it wasn't waiting 1 second from the beginning of one sound to the beginning of the next, right? It was waiting 1 second between sounds. And the difference is what was happening is when you use the Matlab built-in sound function, it waits till the end of the sound playing to go on to the next line, right? So we got to the end of the sound, then waited a second, okay? Which led to it being like actually much slower than I expected it to be. So let's make our first major change here and change from using Matlab's built-in sound function to Psychtoolbox's sound functions. So this requires, and I regret to inform you that this is another case where doing it in Psychtoolbox is a little more complicated than doing it in PsychPortAudio, but more powerful. So it's called PsychPortAudio. Is the there have been various systems for playing sound in Psychtoolbox over the years, but this is the current version. In theory, I was going to Google it for you so you could see the documentation, but it looks like our Wi-Fi may be acting up. So, oh, there it goes. So it has various functions. So it's called PsychPortAudio, and you can do things like basically open, which means sort of like open a sound playing device. And then you can, basically what you do is you open a sound. You can think of it like a sound object, although like I said, Matlab doesn't use real objects for this stuff. You can open a sound object. What you then usually do is fill up its buffer, meaning you've sort of created a sound device, and then you want to fill it with data. So you're going to create this device, fill it with data, and then what you're going to do is at some point tell it to start playing whatever you filled up, whatever data you put in the buffer, okay? So it's a multi-step process. This is what PsychPortAudio is really basically doing when you just create a sound object in PsychPortAudio, but it sort of doesn't make you go through all the different steps. So Psychtoolbox makes you manually go through all these steps, like first create something to play a sound, then fill it up with particular sound data, then tell that sound data to start playing. The advantage is, this is much more flexible. So you can use the same device and you can delete everything in it, you can fill it up with something else, et cetera, et cetera. So you can do a lot more. You can schedule a sound to play at a particular time in the future, which is kind of cool. You do all kinds of cool things. But we're going to use a pretty basic version of it for now. So anyway, so the most basic version, if we go to actually the documentation for opening a sound device, again, you can see Psychtoolbox has a bunch of optional things. So basically you can tell it a device ID, that's if you have a bunch of different sound devices on your system. You can tell it a mode, which means do you want to play sound, do you want to record sound, do you want to simultaneously play and record sound? Usually we just want to play sound. Latency class, I don't even remember what that does. The important things are you want to give it a frequency, which is the same as what we give Matlab, and a number of channels, which is either mono or stereo, right? So in this case it's 1. And again, this is more powerful than I think what you can do in PsychPortAudio, because if you had Dolby 5.1 sound and appropriate hardware, you might be able to play it with, I think you could play it with PsychPortAudio. But we don't, so we're just going to use the very basic version of this. So what we're going to do here is, actually before our for loop, let's create a PsychPortAudio like sound, again, I'll call it a sound object, but it's not really an object in programming speak. It's like a sound handle. So I'll call it my sound, and that's going to be equal to PsychPortAudio. And notice that PsychPortAudio is kind of like screen. Remember, screen is like one function, and then it has a bunch of sub-functions, so you have to tell it with a string which sub-function to do. So we're going to first tell it, the PsychPortAudio function, I want you to do your open thing. And I don't really care about the first variable, which is which device to use, so I'm just going to give it an empty matrix, which is fine. You can have an empty matrix. That means use the default. And I don't care about the second argument after open, which is mode. Mode defaults to 1, which is sound playback only. So we could have put a 1 in there, or we could have just put an empty square brackets because, you know, we want it to just do sound playback only, which is the most common thing. The next thing is, latency class. So if you look down here, actually I remember what this is. This basically means like how much do you want Psychtoolbox to take over your computer in order to ensure good sound timing. Let's do a 1, which is a moderate amount of takeover. So that's these are good default settings for most uses. And then it wants to know the same thing that Matlab wants to know, which is the sampling rate. So how fast to play those samples in your sound data, and the number of channels. Well, Matlab doesn't specifically ask for the number of channels, but the number of channels is 1, because our sounds are mono, right, not stereo. So let's tell it that. That's all we really have to tell it. We could tell it some other stuff too if you look up here. The ideal buffer size, suggested latency, blah, blah, blah. Special stuff. There's all kinds of stuff you could do. There's all kinds of bells and whistles and special features, but this is fine for what we're doing. So basically, we've created a PsychPortAudio device with a sampling rate of whatever's in our data. Oh, shoot. Well, let's do it Let's do it after we read in the sound file. My bad. I'm going to change this up a bit later, but for now, let's do it after we read in the sound file, right? Because we don't create sampling rate until this line. So then let's create a PsychPortAudio sound at that sampling rate with reasonable values for number of channels and everything. And then what we do if we want to play it is we're going to call the PsychPort. Oh wait, sorry. We have to do one other thing. We have to fill up its buffer. So that's PsychPortAudio parentheses fill buffer. Remember, that just means put data, like load up this sound device with data that it will play, but don't play it yet. And we're going to fill it with, well, so first thing you have to tell is which device or which sound device to use. So that's going to be my sound. The second thing you have to tell it is, what is it? The sound data. And one tricky thing, I believe, double check that this is true. Yep. One tricky thing is that PsychPortAudio, this is kind of a dumb thing. So if we look at what our sound data is, it's a 9537 by 1 matrix, right? So if I want to print it out to the terminal, it looks like that, right? So it's a bunch of numbers, all in a column, right? One sort of dumb thing, I don't know why this is that Matlab puts it that way. Psychtoolbox expects it to be as a column, so expects it to be a 1 by 9537 matrix. However, if you want to flip a matrix so that columns become rows and vice versa, super easy. You do sound data, and you put a little apostrophe at the end. That's the transpose operator. That turns your rows or your columns into rows and your rows into columns. If you want to see an example of this, let's call it. I'm going to call let's call it like A. Let's make some random data that's a 5 by 2 matrix. This will make it more clear. So A is a 5 by 2 matrix, 64, 48, 93, 19, 3309, 24, 79. A transpose, or A apostrophe, is just the same data, but where rows become columns and columns become rows, okay? It's a little weird trick. It's a sort of annoying thing that you sometimes have to deal with, where something expects a big row, some things expect a a big column. Some things expect a long row. So anyway, we have to fill up the PsychPortAudio buffer with the sound data, but we're going to have to put in that little apostrophe or it's not going to like it. Okay, so we filled up the buffer. That's all we need to tell PsychPortAudio fill buffer. And then what we're going to want to do is start it playing, which is the start subfunction of PsychPortAudio. And then all we have to tell it is the sound to start playing, because we've already told it what data to put in that sound object. Let's get rid of the old Matlab version of playing the sound. And let's see how this differs. So if I've done this all right, again, warning to the podcast people, here we go, here's some sound.
Ga, da, ba, ga, da, ba, da, da, ba, ba.
Okay, and you notice that Psychtoolbox sometimes spits out a whole bunch of like text output about what you're doing, and that's okay. I mean, we don't need to worry about most of it right now. But what you probably noticed there, was that the time in between each syllable was much shorter this time, right? Because PsychPortAudio, when you tell it to start, it starts the sound playing at that exact moment, but it also immediately goes to the next line of code and continues to play the sound in the background, right? So when we wait 1.0 seconds, that's 1.0 seconds from the beginning of one sound to the beginning of the next, right? So, so we don't have 1 second between the end of one sound and the beginning of the next. We have 1 second between the beginning of one sound and the beginning of the next. Is this working okay for people so far? Do we need to take a stop and debug break? Anybody having problems that we need to stop for? I don't know. Everybody good so far? Okay. Well, if that's the case, then let's proceed. So I'm going to make one, before we go any further, before I add any new features, I'm actually going to make one correction to make this code better that's not going to actually change the function. Anybody see something that's not ideal about this algorithm for playing these sounds? Even if this is all we're doing, anybody see something that's sub-ideal about what we're doing? We got any ideas? Okay, so one thing we're doing is, so if we step through this algorithm, we're picking a random sound number, creating a file name, reading that file into memory, creating a sound device, filling the buffer, starting the sound playing, waiting, and doing it all again. There's nothing really wrong with this, but one problem with this, or one sub-ideal thing about it, is we're doing a lot of work that we actually only need to do once. So if we're going to play the same syllables over and over again, we could just read them all from disk one time and just select the data from one when we need it, right? So that's one thing we could do. And another thing we could do is only create one PsychPortAudio device. So only open it once and just change what's in the buffer after every time we play it. So we could only have one open command in here. So let's see if we can do that and get the same result with, you'll see that we actually might not cut down any lines of code, but what's in here will run slightly faster because we don't have to read off the file every time we play a sound. So what we'll want to do in order to do that, we'll want to preload our sounds in, right? So instead of reading a wave every time, we only have to read each wave once and then store it in memory. And these are tiny files, so it doesn't really matter how much memory we take up. So let's do a for loop. So we've just defined in syllables as how many syllables we have, ba, da, and ga, right? So let's say for I equals 1 to n syllables. So this is before we start looping through trials. I'm going to go ahead and type my end so I don't forget to end the for loop. So let's take this line out of here. So our first file name, so what we're going to do is load in ba, dot, and ga, dot wave in sequence, right? So if I is our for loop variable, right, it goes from 1 to n syllables, it goes from 1 to 3, so it'll be 1, then it'll be 2, then it'll be 3. So we really want to say, each time we go through the for loop, our new file name is going to be the ith syllable First ba, then da, then ga, with dot wave on the end. So we'll do that. We'll just take this line out, this wave read line, stick that there. And then what we basically want to do is we want to have a variable that stores the sound data. Ideally, we want a variable that stores the sound data, or a matrix that stores the sound data from all three of these sounds, right? Now, there's only one problem. So we saw that the sound data from ba.wave is 9,537 samples long, right? Or 9,537 data points long. Let's try seeing how long da.wave is. Let's call it sound data 2. Sound data 2, they're about the same length of time, but slightly different, right? So one is slightly longer than the other. Looks like ba is slightly longer than da. What that means is, you would think this might be a perfect circumstance for us to have a 3 by 9,000 and something item matrix with the three sounds, each in one long row of that matrix, right? But the problem is each row does not have the exact same number of entries in it if we do it that way, because the different sound files have slightly different numbers of samples in them. So there's a couple things we could do. One would be to add some zero samples onto the end of the shorter sound files so that just, pad out with zero sound so they're all the same length. That's one thing we could do. Another thing we could do is just use our new friend, the cell matrix, and put the matrix from each piece of sound data into a cell matrix, okay? And so then the cell matrix can have this, this row of sound data. It can have 3 of those individual rows of sound data, and they don't have to be the same size, because the cell matrix doesn't care what each of its items is, right? It can hold any type of matrix in each one of its elements. Okay? So the only thing we're going to have to do that, if we want to build up a cell matrix, we're going to have to create an empty one at first and then add on to it, right? This is just like what we did in Python. So let's call it like sound cells or something like that, just to make it clear that this is a cell matrix. And I can create an empty one with just 2 empty curly braces. So if you want to see like, sound cells equals this. So it tells you sound cells is equal to that. If you want to get the size of the empty matrix, it says it's a 0 by 0 matrix, right? But it's still a thing. It just doesn't have any entries in it. Okay, so we've created an empty cell matrix. And then in Python, what we would do is we'd say like that dot append and then something, right? But what we can do in Matlab, and I think you've seen this trick in the problem set somewhere. I'm going to be giving away stuff from the problem set all over, I guess. We can say sound cells end plus 1 equals sound data. Right? So what this is basically going to do is say sound cells end would be the last item in sound cells, right? So what this is basically saying is make sound cells one item bigger and put sound data, which we just read in from the file, put that sound data in the new element that we just created, okay? So for example, let's make a variable called myCell, and it's equal to, let's call it 64, and then the letter A, and then true. Okay, so it's got 3 different types of data in it. It's a cell with 3 items in it, 64, A, and the number, well, the true value, which is 1, right? So if we want to get the first item in myCell, we can do myCell1. If we want to get the last item in myCell, we could call it myCell3, right, which is the value 1. But if we don't know how many items are in myCell, we still want to get the last item, we could also just call it myCellEnd, right, which gives us that value of 1. So you can use end to refer to the last item in the matrix. And now if you do end plus 1, it'll give you an error because we don't have end plus 1 items in my cell yet. But if you tell it, I want the end plus 1 item to be something, it's smart enough to know that what you mean is I want to add an item and stick stick that value into the new position, right? All right, so that kind of gives you an answer. If that doesn't make a ton of sense, that's okay, because we're kind of asking what n does on the problem set, I think. But that should end up giving us a cell matrix with 3 items in it. Each one of them has sound data in it. Okay. I was going to sneeze. Okay, no sneezing. So what I can do now, actually, is I can also take the creation of my PsychPortAudio line. I can take that out of my loop, because I only need to create it once. Now note that I have to give it a sampling rate. And one kind of shady thing I did in this loop is I just overwrite the value of sampling rate and in bits every time. So one assumption, just to be lazy, we're going to make in this file is that all of our sound is encoded with the same sampling rate and number of bits, right? I'm just going to use a single value for that for all the sounds, rather than make another matrix with each sound file sampling rate and each number of bits. So we're going to kind of cheat and do that. But now we've got all the information to open our PsychPortAudio device, which means we can trim out some lines from our for loop. And importantly, oh, sorry, there's a couple other things we want to do. Remember that when we filled the buffer of our PsychPortAudio, we had to flip the sound data, right? Everybody remember that? I'm just going to move that flipping from here up to here so we don't have to keep flipping it. We just put it into our storage matrix flipped, okay? Or transposed. And then the other thing we have to do here is instead of referring to sound data, right, which was what we read out of the sound file, we now want to refer to the audio that's in one of our sound cells, right? So what we have the number, 1, 2, or 3. Sound cells should now be a 3-item matrix, each with a line of sound data in it. So we can just do sound cells, curly brace, sound num. And that should refer to the first, second, or third item of sound cells, each of which is full of sound data. Now in theory, let's test this out. Watch out for sound on the podcast.
Da, da, ba, da, ga, da, da, ga, ga, ga.
Okay, cool. Yay, so it works. Now let's, we don't have a lot of time to, so far we haven't done anything but play a few sounds, I realize. But we'll get into more, maybe we'll continue this demo next time. But let's do one more little exercise before we stop, just to sort of help you understand what's going on here. Let's turn on the debugger. I'm just going to set a breakpoint on the first line and run this again. And just kind of, if you're not getting how this code works, let's just kind of quickly step through. I'm just going to use this step command over and over again. I think for you guys on Windows, it's F10. I'm going to use the keyboard shortcut so that so I don't have to keep going to the menu. But let's just step through and see if it makes sense to you what is in all these variables as we step through the code. So I step through this line. See that syllables is a 1x3 cell, right? With 3 entries, ba, da, and ga, 3 strings. I set number of trials equal to a 1x1 matrix of numbers, which is just the number 10. N syllables equals length syllables, says that n syllables is now 3 because that's the length of this 1x3 cell matrix. Sound cells becomes an empty 0x0 cell. Then we do a for loop. First we make the file name, ba.wave, right? Because syllables, I. Syllables is ba.ga. I is 1, so syllables 1 is ba. Add a dot wave, that gives us ba.wave. Read in the sound data, sampling rate and number of bits using wave read. So we get a 9537 by 1 chunk of sound data. Sampling rate's 22050, number of bits is 16. And then sound cells n plus 1 equals sound data transposed. Means that sound cells is going to now be a 1x1 cell with a 1 by 9537 row in it, right? So do that again. We see that now we've got 2 cells, or 2 items in our cell matrix. One that 1 by 9537, the second one's going to be now 1 by 9453. Do it again. Now we've got a 1 by 3. The third one is apparently 9,675 samples long. Create a PsychPortAudio sound. you see that it's just the number 11, right? That's what I mean when it's like a claim check at a coat check or a dry cleaners. It's like Psychtoolbox just knows this is sound device number 11. Who knows why it picks 11, right? And maybe it's the 11th one I've created since I started up. I'm not sure. But anyway, it's just a way to tell Psychtoolbox which sound device to be using or which sound object to be using. Then we're going to do a for loop through each trial, pick a random sound num. In this case, we've got 1. Fill the buffer of the PsychPortAudio device.
Ba.
Start playback, wait 1 second, and then repeat that 10 times, right? Does that kind of make sense to people using the debugger to step through? So you can kind of go through again. Sound num is now number 1 again.
Ba.
Fill up the buffer, play it, wait a second. Sound num is another random number, this time it's 3. That means we fill the sound buffer with sound number 3.
Ga.
That's ga. Wait a second, and so on. Okay, so just we'll forget about doing that anymore. Any questions about that so far? We didn't get super far with that, but that's okay, I think, because I wanted to kind of step through the cell matrices and step through the basics of Psychtoolbox with you guys. So we'll get more into that next time, maybe, and sort of integrate this with a full task and some responses and timing and so forth. So any questions? Okay, so just save that. Feel free to play around with it a little bit. I'll put the code so far online tonight. And then in 2 weeks, I guess, in a fortnight when I get back, we will resume with this demo and sort of build on some text, build on some collecting responses, build on some more sophisticated timing than just doing wait secs, and go from there. Okay? And I will probably, on the next problem set, ask you to kind of do some kind of Psychtoolbox tutorials with visual stuff and pictures and things to kind of let you practice Psychtoolbox even when I'm not here for the lectures. Okay, so that's it. Let's end for today.